jet lag, sorry, is Musco. He talks up lecture 2 about linear systems, recent developments.
Thanks, Peter. Yeah, so the goal of this talk is to follow up on Mark's presentation. To give some context, like I don't want to pin myself to a specific research area, but my background is in theoretical computer science. So this talk is going to be more focused on like recent developments and algorithms for solving linear systems and also some open questions. Those are going to be heavily biased towards sort of like the ATCS way of asking questions about these problems, which is, I think, part of the goal of this talk is to give you a sense of like what people in that community are interested in. OK, so just for some basic setup, in the typical numerical linear algebra setting, we're trying to solve systems, a system AX equals B. And while you could ask about like solving systems over general fields, in numerical linear algebra, people are almost always thinking about A and B as having complex or real valued entries, and you're trying to solve the systems over the complex numbers of the reals. It might be that your input is represented approximately in some way, and your computations are approximate. So things are like represented fixed point arithmetic or floating point arithmetic, but your goal is to get an accurate solution to the problem over the reals. For this talk, I'm not going to bother too much about models of computation. So if you're a non-expert, you can think of all the algorithms I'm going to talk about is running in what we would call the real RAM model, where you're allowed to do exact arithmetic on numbers. You can exactly add, multiply, divide numbers. There will be places in the talk where it's important. An algorithm that works in real arithmetic will not work on a finite precision computer, and I'll point out those cases when they come up, and that will lead to some open questions we talk about. But try not to bother thinking about floating point or finite precision, all this stuff, when I'm presenting the algorithms. OK, so yeah, I want to solve systems. As Mark already introduced to us, you always have one default option, which is doing a direct method like Gaussian elimination. You take a matrix A, you factor it in such a way that you can do efficient linear system solves using that factored matrix in order n squared time. So the standard methods like Gaussian elimination would take n cubed time to do the factorization. But as we saw like yesterday, you can speed this up using fast matrix multiplication methods to get order n to the omega time. OK, if you want to solve a general system, like without any assumptions on the system, n to the omega time is the best we know how to do. There's open questions, open complexity theoretic questions here. For example, we suspect that solving linear systems, very general linear systems, is as hard as inverting a matrix, which is as hard as multiplying two matrices together. But there's not, oh, this got cut off, actually. So what did I do here? OK, now it's not cut off. OK, but for example, an open question is, if you could find an algorithm that ran in faster than n to the omega time for solving general linear systems, would that have any implications for faster matrix multiplication algorithms or faster inversion algorithms? We don't know if that's the case. OK, so presumably the problem could be easier. But as of now, if you want to do general linear systems, that's the best you have. So when people talk about faster methods for solving linear systems, they're almost always talking about doing it under further assumptions on A. And assumptions on A can take roughly two flavors. I will call some assumptions spectral assumptions, which are assumptions about A's eigenvalues or singular values. Or as Mark pointed out, you can go a little bit more general than that, things like the numerical range and things related to the numerical range. There's also structural assumptions, which in some sense are much stronger and often about what format the entries of the matrix take. Is the matrix sparse? Does it have some low-rank structure or hierarchical low-rank structure? Is it have decay away from the diagonal? So these are a bit more, like fine-grained assumptions. And there's a ton of work on finding faster solvers under like either class of assumptions. I'm going to start by talking about spectral assumptions. In particular, I'm going to try to do a review of Krylov subspace methods and try to give some worst-case bounds that depend in a simple way on the singular values of A. So any matrix A, whether it's symmetric or not, I'm going to think about real valued matrices to keep everything simple, has a singular value decomposition, but this would also hold for complex matrices. U, sigma, V transpose, where sigma is a diagonal matrix, and U and V transpose are orthogonal matrices, n by n orthogonal matrices. On the diagonal of that diagonal matrix, I have the singular values, sigma 1, sigma 2 through sigma n. And I take as convention that like sigma 1 is the largest, sigma 2 is the next largest, and so on and so forth. OK, so we're going to try to write down bounds for solving systems that only depend on these singular values. One thing to keep in mind here is when you want to prove worst case bounds, there's a trade-off between the precision of the bound you prove and the simplicity of the bound you prove. So the bounds I'm going to present are erring on the side of more simple and less precise than something like what Mark talked about, where you're depending on, say, the spectral, like the spectral radius or something like this of the matrix in the numerical range. Okay. And we'll present bounds that come from understanding the Krylov subspace method, so hopefully some of this will reinforce what we saw at the end of Mark's talk. Okay, so here's a standard result. Let kappa, which I'm going to denote as the condition number, be sigma 1 over sigma n, the largest singular value over the minimum singular value. This is consistent with the notion of condition number we've seen in the other talks, like sigma 1 is the spectral norm or the operator 2 norm of A. And 1 over sigma n is indeed the operator 2 norm of A inverse. So this is the same condition number that people have been talking about throughout, okay? So standard result is if that's your condition number, if the cost of multiplying a vector by A or A transpose is written as MV of A, matrix vector cost for A, MV of A is always bounded by n squared, then it's always possible to find an x tilde, which is an approximation to the true solution we want, A inverse minus B, with epsilon error. In time, that depends on the cost of multiplying by the matrix times kappa times like a log factor that maybe involves kappa in the accuracy. So it's always better than n squared times kappa times log kappa over epsilon. Okay, so when you compare this to the direct methods, ignoring the log factor, this is roughly faster than like Gaussian elimination when your condition number is bounded by n, okay? So this bound, we're going to talk about how you achieve this bound. It can be obtained by many, many Krylov subspace methods. So we learned what those were in the last talk. I'll reiterate it. Accelerated gradient descent, the conjugate gradient method, Chebyshev iteration, the LSQR method, all can obtain this sort of worst case bound, which gives us a starting point. It's a simple to state bound. It just depends on that simple condition number. It gives us a starting point for designing new algorithms or asking new theoretical questions. Okay, so yeah, one point I'll make, which we'll see in a second, is that if A is positive semi-definite, so it's symmetric, all of the eigenvalues are positive, this kappa can be replaced with the square root of kappa, okay? And actually, the way we will prove this bound for all matrices is by reducing to the positive semi-definite case. So someone asked at the end of the last lecture about passing to the normal equations. I'm going to assume we do this. There are many reasons you might not do this in practice. It might not give you the sharpest convergence. It might be expensive to multiply by n transpose. But it's a way to get clean worst case theoretical bounds, and it gives you, and for many problems, it gives you good fast algorithms. Okay, so the point here is I want to solve AX equals B. I can always instead solve A transpose AX equals A transpose B. A transpose A is a positive semi-definite matrix. Okay? Now, when I do that, what are the singular values of A transpose A? They're the same as the eigenvalues because it's symmetric, positive, semi-definite. The eigenvalues are the squared singular values of the original matrix A. So I square the condition number, okay? So what, oh yeah, go ahead.
I assume you want A transpose A to be positive definite.
Yeah, positive definite. I think I said semi-definite, but I mean positive definite because it needs to be invertible. Yeah, absolutely. Thank you, Ann. Okay, so those are the squared singular values of the original system. So if I can show that we can get a bound that depends on square root of kappa for all positive semi-definite matrices, it of course applies a bound of kappa for all matrices for solving the system. Okay, any questions at this point? Okay. So what's the idea behind how we're going to obtain such a bound? We're going to do so by using a Krylov subspace method. And Mark already told us what these methods are, but let's reiterate it. The Krylov subspace is the space spanned by the vectors b, ab, a squared b, all the way up to a to the tb for some iteration count t that the algorithm will need to run for t iterations. And the goal is that we're going to try to find a solution to our linear system in the Krylov subspace. So another way of stating this is let Q be a matrix with orthogonal columns that spans the Krylov subspace. I'm going to, instead of finding x such that ax equals exactly b, I'm going to find some matrix in that, some vector in that span, which could be written as, say, qy, So the height of y here would be like t plus 1, such that a qy approximately equals b, and this qy will ultimately become what I return as my x. OK, so for Krylov methods to work well, we need two things to be true. We need that the Krylov subspace actually contains a good approximate solution, x tilde. So like if there's nothing in the span of Q which gets me close to B, we're screwed. And additionally, if we actually want a fast algorithm, we need to be able to rapidly extract the solution from the subspace. Okay? So Mark hinted that he's going to talk more about methods that can let you do this tomorrow, but I'll also brush on those today. Okay, so yeah, what do we mean by efficiently extract the solution? Well, the cost of building a span for the Krylov
Sorry,
yeah, go ahead.
Question.
Yeah, go for it.
If you allow t to be, I guess, n or whatever,
Yeah.
are you're guaranteed that the solution lies in the subspace?
Yeah, this is a great question. So we're going to cover this. If t equals n, in principle, if everything is an exact arithmetic, the solution will lie in the Krylov subspace. And indeed, this will lead to algorithms that are faster than n to the omega time, so for sufficiently sparse systems. However, this blows up when you have to use finite precision. So like a big open question is, are there algorithms that obtain those runtimes when you have finite precision? But we'll talk in more detail about it. It's a good question. Yeah. Yeah.
And I guess B could lie in like some invariant subspace, right?
B, say that again?
Like B could be an eigenvector so that you wouldn't go there.
Oh, sure. If B is like an eigenvector or it's spanned by like a small number of eigenvectors, like say k eigenvectors, you will actually terminate even before you get to n. Yeah, but typically this isn't the case, but you might get lucky. Okay. Yeah, so we need that there's a good solution in the Krylov subspace. And for us, that's going to mean not that we're going to take it all the way out to n. It's going to mean that hopefully we get a good solution as soon as t is roughly square root of the condition number. That would be what we mean by good. And for efficiently extracting the solution, we're going to ask for something very ambitious. Constructing the Krylov subspace, how much time does it take? Every time I get a new vector in the Krylov subspace, I need to multiply a by that vector. So I have cost mvat just to build the vectors in the Krylov subspace.
Sorry, why would you expect the...
Okay, good question. For some problems, you might just get lucky and it's well conditioned. The other reason we care about this is there's a whole sort of industry for developing preconditioners. So as Mark pointed out, you can often, by knowing something about your problem, pre-multiply on the left to reduce the condition number to something that's small. And then if you can do that, you want something that depends on the condition number.
So some preconditioning to force it to be.
To force it, yeah. But still, like you might not be able to force it to be 2. You might not be able to force it to be 3. You might force it to be 1,000. So in that case, you still want to have a good dependence on the condition. Yeah. Okay, so to point 2, when I talk about efficiently extracting a solution for the Krylov subspace, I want it to be very efficient. So I'm actually going to shoot for run times. We'll get to this later. Roughly on the order of nt. The cost of doing a multiplication with A could be as small as n. Think of a matrix that's just like a diagonal matrix if you're doing like sparse multiplications. So like I roughly think of a rough lower bound of mvat is like nt, and I'm going to try to like have my post-processing cost to extract the vector from Krylov subspace be essentially as low as that minimum cost. Okay. So let's talk about the first point first. How do we ensure there's a good solution in the Krylov subspace, meaning that after roughly t equals square root of kappa iterations, we get a good solution? Yeah, I'm going to reiterate with what Mark said. We are returning a solution of the form x tilde equals qy, where q is a span for the Krylov subspace. What that means is that x tilde is a linear combination of the vectors that comprise the Krylov subspace. So I could write x tilde as some polynomial in A, where the coefficients are the same as the coefficients that would recombine those vectors in the Krylov subspace, times b. Importantly, when we write p of ab, this is not like a polynomial in the entries of A. P is a scalar polynomial, and we're just applying it to A by like plugging in A everywhere you would plug in x. If you're computing like x cubed minus x squared plus 1, you'd plug in A everywhere you had x. Yeah, I'm going to use this to mean like it's an actual matrix that gives me an orthogonal span for this. I didn't really have to make it orthogonal. I guess I just wrote it this way. Yeah. OK, so are we comfortable with that? No matter what you do, if you're using a Krylov subspace method, you are returning a solution which has the form P of AB, where degree of P, I'm not going to worry about an off by 1 error, but in my notation, degree of P is like less than or equal to T.
Just for hermitian notation, your P of A
is your K.
Q of A.
Q of A, yeah.
And I use P of A for the residual polynomial.
Yeah, OK. And in my, I think Mark's K was my T. Yeah, but yeah, K minus 1 is my T. Yeah. OK. So you're returning a polynomial in the matrix. How can we understand if there's a good polynomial that gets me good error in terms of solving the linear system problem? Well, I want you to think about what a polynomial in the matrix A looks like. So I've moved to symmetric positive definite matrices. So my eigendecomposition is of the form V, diagonal matrix V transpose, where V is an orthogonal matrix. And when I do polynomial of A times a matrix, I mean, what's A squared? This just equals V, my diagonal matrix V transpose, V, my diagonal matrix V transpose. The V's cancel out. You're left with V, diagonal matrix squared, V transpose. And you can do that for all the monomials. So if you just think about it for a minute, polynomial of A is a matrix whose eigenvectors are exactly the same as those of A. You just provide a polynomial transformation to the eigenvalues. OK? And similarly, what I'm trying to do is I'm trying to apply A inverse to B. What is A inverse? It's a matrix whose eigenvectors are the same as A, except you apply 1 over x to all of the eigenvalues. So you invert the eigenvalues. OK. So now I want to understand, is there a polynomial such that A inverse minus B minus polynomial of AB is small? How can I do that? The first step we'll do, similar to Mark also did this, is we will pull out B. So this is certainly bounded by the spectral norm or the operator L2 norm of A inverse minus PA times the norm of B. And then this is going to be something which is easy to understand. OK, in particular because A inverse minus PA has a nice clean form because they share eigenvectors. OK, so let's just look at it. If I look at PA minus A inverse or A inverse minus PA, this is just the same as V, and then V transpose on the outside. And on the inside, I get a diagonal matrix where I have P lambda I minus 1 over lambda I, P lambda 2 minus 1 over lambda 2, all the way down along the diagonal. OK, I want to claim that the spectral norm of that matrix is small. What is the spectral norm of that matrix? Well, it's unimpacted by these orthogonal matrices on the outside. So it's the same as the spectral norm of the matrix, the diagonal matrix. It's just the maximum entry along the diagonal. So in other words, it's the maximum over all I of 1 minus lambda I minus P lambda I. And then I would get times the B there. OK, so I get a good lower bound, a good error bound, as long as there exists a polynomial which approximates 1 over x, the function 1 over x, well on my eigenvalues. So if that was less than epsilon for all eigenvalues, I would get epsilon times norm of B. OK, make sense? Yeah, so how can we understand this problem? I'm thinking about a scalar polynomial approximation problem. I have plotted the function 1 over x. And I want to come up with a polynomial approximation to that function. So it might look like something. This is my best effort at drawing a polynomial. Something like this. And it's not going to be exactly 1 over x, but I want that there exists a polynomial that is close to 1 over x on my eigenvalues, which I've drawn by these points on the line. OK. How can we get an upper bound on this? You could try to be very precise. You could look at the specific eigenvalues and try to understand what's the best polynomial that approximates 1 over x on them. If we had 1 over x minus 1. Oh, because you're saying do Taylor expansion or something. Yeah, so we will do almost exactly that, though. Because if you can do 1 over x minus 1, you can just flip the polynomial. So yeah, good. We're going to do something that is more akin to doing what you would do if you were thinking it Taylor expansion. I'm going to try to find the polynomial, which is not good just at the eigenvalues, but let's simplify the problem if making it a bit less precise. Let's try to come up with a polynomial that approximates the 1 over x function everywhere in the range between lambda n and lambda 1. Okay? So this polynomial, maybe I didn't draw it too well. It would have been OK if there are no eigenvalues in the middle to have it like diverge here. I'm going to say let's be a little stricter, and I want to approximate on the whole range between lambda min and lambda 1. And the key claim here to get a convergence bound is you can just use polynomial approximation theory. So the claim is that there is a polynomial of degree square root of kappa, which kappa reminds you is lambda 1 over lambda n, which uniformly approximates 1 over x to error epsilon times, you pick up a term depending on like 1 over lambda n, but I'm not going to care, this is eventually going to go into a log, epsilon times 1 over lambda n on the interval lambda n through lambda 1. OK, so how do you come up with such a polynomial? This one's actually like not hard to prove yourself, but like it's not something I want to do today. But if you look at like any approximation theory text, like approximation theory and approximation practice is the one that's on my desk, you can easily derive this bound. Taylor approximation is actually a good start. So if you wanted to just do Taylor approximation, and you would do it, you could either do it of like 1 over x minus 1, or you could do Taylor approximation 1 over x about lambda max. You would almost get this bound. You would just get a kappa instead of a square root of kappa. And then you can improve on this using like fancier methods, like basically accelerating the Taylor approximation. But it's a standard bound, and it's also known to be tight, so you can't do better than this. You can use basically a Chebyshev polynomial, and then you have to, you can use a shifted and scaled and appropriately like divided by x Chebyshev polynomial. Yeah. Mark framed a slightly different polynomial approximation problem, which is the way I think about it is find me a polynomial that, he flipped it, but find me a polynomial that goes through 0 and then is close to 1 on the range of the eigenvalues. The best polynomial for solving that problem is a Chebyshev polynomial. And when it goes through 0, it has no identity term. So you can just divide it by x, and then you will get a good approximation to 1 over x. So that's one way to do it. Those details don't matter necessarily. Yeah, go ahead.
So Chris, it looks like your Q comes from trying to minimize the error, the norm of your x minus x hat.
Yeah.
And is that, how are you going to approach computing that like metric, right? So one of the reasons you go through the residuals that we can compute b minus a x hat.
Yeah, so I'm not going to worry about it because like I'm going to push everything into logs. So somehow like if I can minimize, I'm going to get a logarithmic dependence on epsilon. If I can minimize the error or the error or the residual, it's all equal up to like some dependence on kappa. So I can just take epsilon, drive it down to epsilon over kappa, and these will disappear. Yeah, I'm writing it this way because I think if you are not a numerical analyst, the forward error is the easiest to think about. We want to compute A inverse x. That is the problem. So I'm writing this way because I want to give a bound on computing A inverse x. But yeah, as maybe now one day into this workshop, I could have done it the other way. Yeah. Yeah.
Probably worth mentioning the backward error is just the norm of the residual.
Sure. Yeah. Yeah. But we are not going to. Yeah, we're going to push everything into logs. So I'm doing, big O notation. OK, so the claim is we run for square root of kappa log 1 over epsilon prime iterations. I'm writing epsilon prime because I'm going to tweak it slightly. This is how I fiddle around these condition numbers. I will get that the error is less than epsilon prime times 1 over lambda n times b. B I can always write as a times a inverse b. So its norm is bounded by norm of a times norm of a inverse b. Norm of a equals lambda 1. So this is less than epsilon prime times lambda 1 over lambda n a inverse b. So that's the condition number. So if I just set epsilon prime like to be epsilon, I wanted to write epsilon, there are no prime, epsilon over the condition number, we will get epsilon relative error with number of iterations that scales as square root of kappa times log of kappa over epsilon. Okay, and recall that that's for positive definite systems. If you do it for general systems, then you're going to have, you get a kappa instead of square root of kappa. Okay, does that make sense? all I've claimed for you at this point is that there is a good solution in the Krylov subspace. So I just said there is a polynomial. This like you can get it from the Chebyshev polynomial in the Krylov subspace. One legitimate option here is if you know lambda min, sigma n or lambda n and lambda 1, you can actually just compute that polynomial. And you could construct it from the Krylov subspace. But this will give the same bound I have. This is typically not what people do in practice because it's often that you can do with little cost, you can do better. So in particular, one thing people often aim for, and this is what methods like conjugate gradient or GemRes will achieve, is we want to find the best solution in the Krylov subspace, which is always going to be better than any fixed polynomial you could have used. And we're actually going to do it without knowing anything about the eigenvalues. So we're going to find the best polynomial in the Krylov subspace without knowing lambda n, without knowing lambda 1. You might actually think you would need to know all the eigenvalues to do that, but we're going to be able to find the best solution without doing that. OK. And it's not hard to see why you can do this. It's just the least squares regression problem. OK? So I have a Krylov subspace. Presumably, if my algorithm is anywhere near efficient, I've run for t, which is much less than n iterations. So I have a span for the Krylov subspace Q. And what do I want to do? I want to find the vector in Y such that AQY is as close to B as possible. OK? Computing AQ, that's just like you can do that actually with just basically one additional matrix vector product. But either way, it's at most t additional matrix vector products if you're not worrying too much about complexity. And then I need to solve a minimization problem. Find Y, which minimizes this skinny linear system, least squares problem, minimize AQY minus B, and I will find the best coefficient vector Y to get something, the optimal solution in my Krylov subspace. And what's the cost of doing that? This is an n by t least squares problem. I'm not actually going to talk about least squares today, but the cost, if you're not using fast matrix multiplications, is n times t squared, which is hopefully relatively cheap if t is small. OK, hopefully it could be cheaper than your number of iterations. Although it's not always cheaper, right? Like, if t is as large as, I don't know, square root of n or something, this could start becoming a problem. So people care about going faster. I said we wanted to get something where that cost was always a lower order term. It turns out you can actually do this in order nt times. So the cost of matrix vector multiplications to run the algorithm is mva of t, which I always think about as greater than nt. And you can get this cost of computing the minimum down to nt times shaving the t squared. So it's basically always a lower order term, at least if you're doing with positive definite systems and or you're solving via the normal equations. OK. How do you do this? It sounds like Mark's going to go over this tomorrow. So I actually pulled this out of my talk this morning. I'm not going to do the details of this because it would just be doing it twice. There is, and maybe I'll put it as a homework exercise. So yeah, the way that these methods do this is they build a basis, Q bar, for that matrix AQ in NT time. They explicitly orthogonize the matrix in NT time. That's one way you can think about these methods. That's what CG does, what MinRes achieves. And the reason that's possible is because that's not just any old subspace. It has this sort of like recursive structure, the Krylov subspace. And you can essentially show that you can orthogonalize it using a 3-term recurrence. So something magical happens. You start going through the columns and orthogonalizing them against each other. And you see that when you get to the kth column, it's already orthogonal for free to the earlier columns, like anything before k minus 2. So take that as a hand wave. Mark will show you in detail tomorrow, and you'll understand why you can do this efficiently. But you can do it in NT time because this Krylov subspace is so structured. OK, so now what's our conclusion? Our total cost to build the Krylov subspace is in orthogonized Krylov subspace, and therefore find the optimal solution of the Krylov subspace is mv of a times t plus nt, which I'm just always going to think of as order mv of a times t, because certainly mv of a is going to be more than order n. OK, so the conclusion is for PSDA, we can solve ax equals b to epsilon relative error in square root mv of a times square root of kappa, log kappa over epsilon time. And then we'd replace that square root of kappa with kappa if it was a general non-PSDA. So it will be better than for PSDA, or positive definite A, it will be better than like matrix multiplication algorithms or direct methods like n-cube methods if the condition number is less than n squared. OK. So a natural question. This is a clean bound. It's simple. There's a lot of methods that can probably beat this bound in practice, but it gives you a benchmark. So question is, can you improve on this bound? Like, could you get a better dependence on the condition number? Could you get like condition number to the 1/4? It's pretty clear if you've thought about Krylov subspace methods, you can't, because for Krylov subspace methods, because the polynomial we found is near optimal, and you always return a polynomial. It's easy to argue that a Krylov subspace method can't do better than square root of kappa. But you might consider more general models of computation. So just in the goal of highlighting open questions, one thing we've become very interested in is matrix vector query models of computation. So the setup here is I have a matrix A. I give you an oracle that computes matrix vector products with A or A transpose. And then you can ask, is there any algorithm that interacts with such an oracle and uses less than square root of kappa, roughly, matrix vector products to solve a linear system? Okay? So this matrix vector query model of computation is more general than the Krylov subspace model. It captures Krylov methods. We're going to hear about randomized methods from Joel. It captures many randomized linear algebra methods. And the other thing is it's strong in the sense that many algorithms we know fit into this model, but it's weak in the sense that it also is like it doesn't capture a lot of other types of computation. And I'm not even counting computational cost, I'm counting query complexity cost. So unlike general like Turing machines or circuits, we can prove very strong lower bounds in this model using information theoretic techniques. Okay, so what is known for the problem of solving AX equals B? At least if you're parameterizing that problem by the condition number, you can prove that if you want to solve that to a constant epsilon accuracy, you require square root of kappa matrix vector products with a positive definite A, no matter how you come up with those. You could use a randomized method. It could be a Krylov method. No matter what method you do, you can't beat what Krylov methods do. So this was a result of Braverman, Hazan, Simchevitz, and Woodworth from 2020. Yeah, so
Not necessarily this theorem, but
in this, it really depends on your model of computation. For this model of computation, and maybe there will be a talk about this at some point during the semester, the main techniques are people use like communication complexity lower bounds, which is like a rich field in theoretical computer science, or hypothesis testing lower bounds from statistics. So you use a hard instance A, which is like a random matrix, and then you prove that if I could solve the system, I could like estimate some quantity about A, and then you appeal to like statistical lower bounds on sample complexity things. So that's a 10,000-foot view, but for these lower bounds that we know, they're mainly information theoretic techniques.
So this is in this model that you described before. Right?
This is in this query model.
Query model.
Yeah. That's not to say you couldn't come up with an algorithm that runs an n squared square root of kappa time, but does crazy other stuff. Accesses only a few entries in the matrix. Doesn't access via matrix vector products, so it's not an unconditional lower bound on the runtime. It's a lower bound in this model. Yeah.
Like in optimization, if you only have access to the gradient, has to also has this lower bounds at one time before. I wonder what makes linear systems kind of more complicated than general optimization.
They're very closely related. So people study query models of computation in other numerical areas. One of the main ones is optimization, where they study like first order oracle lower bounds is what they would call it. I have a function I want to minimize, and what I'm given access to is I can evaluate the function, and I can evaluate its gradient at a point. And then you try to ask, what is the minimum number of gradient evaluations you need? Actually, if you're solving this problem, like solving minimize x transpose AX minus x transpose B, which would solve the linear system problem, the gradient is basically a matrix vector product of A transpose A. So it's very closely related, but one thing that these lower bounds have had to deal with is randomized algorithms. Many of the lower bounds of the optimization people study do not actually apply to randomized algorithms. It's not always obvious from reading them, but that's an additional challenge. Yeah.
And the function's easier because it's a quadratic. Like, it's harder to prove a lower bound because it's a specific.
Yeah, although these like Nesterov lower bounds for gradient complexity, they use quadratic functions. So yeah. Yeah.
Is there still a logarithmic gap between upper and lower bounds, or did you just...
I need to look more closely at the paper. I suspect, for example, it doesn't capture the log kappa, but I'm also not 100%, which I think should have been in my result. So probably there's a log gap. Yeah.
And if A is not positive definite, do we also have a tight bound?
That's actually an open question. So I don't know how hard that question is, but when I was writing the slides, I realized I didn't know the answer to that, so I wrote it down here. Like, if it's not positive semi-definite, I don't know if the right lower bound is kappa. It should be, and maybe someone can solve that over the coffee break, but it could also be a hard question. So I hadn't thought about it before. Yeah. Oh, you know, Raphael.
No, the thing I want to respond to is I believe the log kappa dependence and log epsilon dependence is open on the square root of kappa.
So our upper bound still has logarithmic determinant?
I believe our upper bound has a logarithmic determinant and our lower bound does not.
Yeah. I think about the square root of kappa is like the most interesting part of the bound, but it's not to say that optimizing log factors isn't a problem. Okay, so I'm just highlighting this model because it's led to a lot of work in recent years. Like with Raphael, we've worked on getting lower bounds for problems like trace estimation of matrices you can only access implicitly, and then a lot of other people have worked on the space. So lower bounds for approximating the top eigenvalue, for doing a near optimal low rank approximation, for estimating the rank of a matrix. Like there's a lot of papers on this in recent years. It's a nice way of studying these problems from a complexity theoretic perspective. Okay. Okay, so I want to talk about something else, which is JM asked, is it reasonable to assume the condition number is less than n? In many cases, it's maybe, I said it's reasonable because maybe you could precondition. There are also many problems where convergence is much faster than is predicted by these worst case bounds, because we were making this assumption that my bound was coming from getting a good approximation on the entire interval. And you don't need that. You only need a good approximation to 1 over x on the eigenvalues of your matrix. So one thing you might be able to do, for example, for this spectrum, it's like a split spectrum. I have a small number of large eigenvalues and then a bunch of eigenvalues that are smaller. I might imagine that I could get a polynomial that approximates well on this part and then just add an additional point of interpolation down on the bottom right and get a good approximation to 1 over x this way. And I'll require a much lower degree than if I tried to get approximation over the whole interval. Okay, so yeah, this is, even if you run one of these Krylov methods, you'll see this behavior. So if you have clusters of eigenvalues or a small number of outlying eigenvalues, it will converge faster than the condition number bounds predict, more depending on the condition number of the lower part of your matrix. Okay, but I'm going to talk about this is out of order. I thought I was going into a different part of this talk, so I'm going to say something totally different. This will become relevant in 5 minutes. But one thing I want to address, yeah, go ahead.
What sort of natural class do you get this kind of behavior where the eigenvalues concentrated in 2 places?
I guess I wouldn't say it's concentrated in 2 places, but you often get matrices with large outlying eigenvalues. Like an example would be an all positive matrix often has one massive eigenvalue that's sort of close to the all ones vector.
Yeah, you can have a bunch of eigenvalues in the middle with an average inside. You're just counting the outliers.
Yeah, maybe you shouldn't have said it's 2 clusters. It's more like you have a well-conditioned part and then some outlying eigenvalues.
That sounds more natural to me.
Yeah. This slide was supposed to lead me into addressing actually another question JM asked, which is this question of, forget about outlying eigenvalues. There is always a polynomial that interpolates the eigenvalues. So there's always a polynomial that actually nails 1 over x exactly, that has degree n. Okay, so what does that tell you? Well, we said if you set t equal to n, my error bound is bounded by the minimum over all degree t polynomials of the maximum error, but that maximum error will be 0 if I choose a polynomial that interpolates the function. So we can exactly solve ax equals b in order mva times n plus n squared time. N squared is like the nt I had before, which at first blush you look at this and you say, wow, that's actually a faster algorithm for solving sufficiently sparse linear systems faster than matrix multiplication time using a method like conjugate gradient. So in particular, if my linear system is sparse, so mv of a, say it has nnz of a, which is the number of non-zeros in the matrix, is less than n to the omega minus 1, multiplying by a will cost n to the omega minus 1. So this cost will be n to the omega. So I get a faster algorithm than n to the omega for matrices that have less than n to the omega minus 1 non-zeros, which is roughly n to the 1.37. As Mark pointed out this morning, in practice, we often think about matrices that have order n non-zeros. So that's actually quite good. Would be faster for matrices that are relatively dense. there's an issue with this, but it leads to some interesting open questions. So in particular, as many people in this room will know, this is a result that holds in exact arithmetic computation, but it completely blows up if you try to do things in finite precision. So the problem is you can prove that to prove this sort of bound, you would need the number of bits of accuracy of your numbers to grow at least linearly with n. So all your multiplications, additions, et cetera, have linear and n cost. You're back up to a cost which is greater than n cubed. Okay? So it does not hold. But you could ask, can I try to get something like along those lines? So just to comment on this, yeah, so the bounds I talked about where you depend on square root of kappa, it's known those hold even if the precision of your numbers, say in floating point, is roughly 1 over poly n kappa. So the number of bits you need is logarithmic in that. So like log of n plus log of kappa. Yeah?
Is there a way to say that something is exactly 0, but other than that, you have, a realistic number of bits of precision? Or there's no way to separate like the equal 0 problem from the...
In this case, it's not a matter of the equal 0 problem. So even if you try to say like I get a constant error solution, if you're only using like roughly like log n bits of precision or even a small polynomial in n, you won't even get a constant factor accuracy.
Okay.
So yeah, I would be happy, very happy if you could get constant accuracy in this time, because actually then you can bootstrap that to get arbitrarily high accuracy. But yeah, it's not a matter of the exact equal 0. It's just like a matter of these polynomials end up being crazy and they can't be well represented in the computer. Yeah, so results like this, that you can get the kappa bounds or square root of kappa bounds, those follow from, it takes effort to prove that those bounds still hold. Right? Then there's a long line of work on that, including by people in this room. So like Anne Greenbaum is our resident expert on bounds for, stability bounds for methods like conjugate gradient. But yeah, these bounds do not hold if you're trying to get the worst case approximating polynomials. So they don't hold if you're trying to get this like order n iteration complexity. But there's been interest in understanding what can you do. So I will highlight a paper with a crazy runtime, but I'll simplify it for you by Peng Vempala from 2018. It was like the best paper at one of the theoretical computer science conferences, SOTA. And they gave this crazy bound where they were trying to say, can I get faster than n to the omega time algorithms for solving sparse linear systems? And indeed, for a narrow range of parameters, they achieved that. So just to give a sense of what this gives, if you have a matrix with order n non-zeros, which is a reasonable practical setting, n by n matrix, their algorithm gives a bound of n to the 2.331, which is indeed slightly better than n to the omega. And this was improved more recently by Nia to be n to the 2.27, which is a little bit better than n to the omega. And the way they do that is it's not totally departuring from the Krylov subspace framework. They use basically a randomized block Krylov subspace method. So instead of starting with b and computing b, a squared b, they start with a block of random vectors, which I'm denoting by pi, and compute successive powers on those random vectors. Yeah. Omega is like the best, current best bound we know how to prove for matrix multiplication, which I realize is not not the definition we used yesterday.
Because omega, no, but then I would take omega to be like 2.7 or something.
Sure, yeah, okay, that's fair, but if you're gonna only consider practical algorithms, I think this method actually isn't that far from being practical, but it's not practical. This method is not implemented. So I think if we're going to do a head-to-head comparison of like the result from like the Peng Vempala, we should use like the sort of like in principle algorithm you could do.
But though you have to deal with matrices larger than the number of atoms in the universe.
Yeah, but I actually like this question because it's also important to say, even if you cannot beat n to the omega, it's really interesting to get alternative methods that can get this low of complexity, right? Because these methods might become implementable before the best fast matrix multiplication methods do. So it's a great point.
Ever becomes.
They might not ever. So if you have alternative methods that can get lower complexity for sparse matrices, this is a really interesting theoretical question. Yeah?
So does this bound apply if I say, I only want to use classical multiplication, I set omega to 3. Does this algorithm, is that true or not?
Yeah, good point. In the algorithm, they use fast matrix multiplication. I think the claim is that if you take their algorithm and you do all matrix multiplications with an n to the q time algorithm, you always get something that's faster than n to the q in the end. but I would need to double check that. I don't wanna
Replace the
promise that.
omega in that upper equation with whatever the runtime of the base matrix multiplication.
I believe that's right, but then we'd have to check that that actually gives something better than, yeah.
Check that there's no rectangular matrix multiplication going on in the analysis.
No, they do use fast rectangular matrix multiplication, but I think if you take all that out, you replace all their matrix multiplications with slow, naive time method, I then think they will get not better than omega bound, but they'll get better than like an n cube bound, and it's another approach to beat it.
I have a question. I mean,
Yeah.
I look at the statement of the theorem by Ping and Impala. There is the condition number in Ping.
Yeah, yeah.
But then you say this gives this upper bound for the matrix, you know, with NNZ. But there is no dependence on condition. So I mean.
Yeah, I'm pushing. Right. So this is only an improvement if the condition number is polynomially bounded in n.
Oh, okay. There's a.
Yeah, yeah. So I'm just brushing that on the rug, but I'm sort of happy with log condition number dependencies because, yeah.
Mildly.
The number of bits in your computer better depend on log condition number. You're gonna get a junk solution at all. Yeah, so yeah. Yeah, and then
What block size did you use?
I do not remember. I should know because I've read
Is
this
it a
paper.
constant or?
No. Oh no, it's not a constant. It scales with. It will be larger as n gets larger.
It's n to some power.
Yeah, it's n to some power. Yeah, yeah. And then Diana.
What makes this impractical to implement?
I actually don't know that it's impractical. I'm just saying I don't know that it's practical to implement, but I think it's not crazy. I think it's basically doing a block Krylov method and then finding the best thing in the Krylov subspace. But one thing is like to get this to work, to get this runtime, they're using like sparse random matrices for the pies, and I can't remember if like their post-processing uses any properties of these. Let's say I don't want to make a claim, but it's to be checked.
It has omega in the complexity bounds. That means it's using matrix multiplication.
Yeah, but as like this conversation was saying, you can implement it without using fast matrix multiplication. You get a worse bound, but it could be faster than Gaussian elimination. Yeah.
Students week have a way to take sparse classical algorithm and fast rectangular algorithm and obtain faster algorithms for rectangular sparse matrices. They use this as a building block.
Wait, what was the first result?
So they take classical sparse, rectangular sparse algorithm or NNZ dependent algorithm combined with rectangular sparse algorithm.
Is it over finite fields or? No, it's over the reals. Yeah, I don't know actually, but we can look at it. There's a lot of work on getting these type of bounds for over finite fields. It's much easier. There's like something called Wiedemann's algorithm. You can get the dream result. You can get n times the cost of matrix multiplication. But yeah, I'll have to look.
So does this imply that as long as omega is bigger than 2, whatever it is, there exists an algorithm that beats it? I'm not.
I think it does, but I need to confirm this. Yeah, I should know the answers to all these questions. I'm not sure. But it's a complicated expression, so I didn't do it. Like I didn't even type it into Desmos. To be sure.
Yeah, I think it does.
I think it does. If it does, they probably claim it in the abstract.
They claim it in the abstract.
Okay, good. Thank you. Okay, I'm highlighting this, by the way, as like an interesting problem where the complexity in the real RAM model is very so if you can do it, you don't need to worry about accuracy of your additions and multiplies is very different than the complexity in a more realistic computation model, which I think is like a rich area for questions. Okay. Yeah, so open questions like can you solve linear systems with n non-zeros in order n squared time? Possibly using fast matrix multiplication, possibly not. Do faster than n to the omega time solvers for say n to the 1.99 sparse systems, imply anything for fully dense systems. There's like a whole sea of questions you can ask like related to these type of methods. Okay, so then I only have a few minutes, but I want to do at least like a couple more sort of like vignettes of research problems. What we were talking about before, I already gave you the preview, is if you have a small number of outlying eigenvalues, methods like conjugate gradient, Krylov methods, they do better because they basically do a good job on this part of the spectrum, then like interpolate that part. Okay? There are a lot of other methods that do better when you have a small number of outlying eigenvalues. So I'm glad Joel will do it for a third time because now that we're in a rush, we'll really breeze through Kaczmarz methods. One of these methods are randomized Kaczmarz methods. So the idea behind the Kaczmarz method is I have a current solution, which I'm denoting as x tilde, and I want to, or I'm denoting as x, I have a current solution x, and I want to improve it so that ax gets closer to b. And one way to do that is you could just like pick a row of A, and you could force that linear equation to hold. So update x so that x times that row now exactly equals, like the ith row exactly equals the ith entry in B, which just requires like finding like the a scaling of that row, which multiplied by that row gets you that the whatever our residual is on the ith entry. So I keep like updating my x vector with this like small x tilde, which is, it's going to be a copy. X tilde is just going to be like a copy of the ith row, till I sort of keep knocking down the size of entries in my residual. So I keep knocking down the size of entries in B. And what was proven about an implementation of this, which uses randomization, specifically, how does it choose the rows? It samples them, and it samples them with probability proportional to their L2 norm. So it takes the ith row with probability proportional to its 2 norm over the Frobenius norm of the matrix. You can prove an exponential convergence bound for such algorithms. So in particular, you can argue that my expected error after t steps is bounded by 1 minus sigma n squared over the Frobenius norm squared to the t times, times a inverse b squared. So we want this to be epsilon. How large do I need to set t for that to be epsilon? Well, if I set t to roughly the inverse of this, I'll get something constant. And then if I multiply that by log 1 over epsilon more, I'll get something that's epsilon. So you need to set it to be roughly Frobenius norm divided by the smallest singular value squared times log 1 over epsilon. Here's one way to think about this bound. The Frobenius norm squared divided by n is the average squared condition number of the matrix, is what I'm going to call it. Sorry, the average squared singular value of the matrix. Okay? Because this Frobenius norm squared is the sum of the squared singular values. So another sort of silly way of rewriting this is I can divide by n and multiply by n. T is n times sigma bar squared over sigma n squared times log 1 over epsilon. This can be improved. So actually, there's fancier methods of these randomized Kaczmarz methods that get you down to sigma bar over sigma n. Oh, yeah. So that's like you sum up the squared entries in the matrix, all of them, but that is equal to the sum of the squared singular values. So yeah, so what I'm writing is like sigma bar squared here equals sum of I equals 1 through n of sigma I squared over n. So the average singular value, which so this is good, right? We previously depended on the maximum singular value divided by the smallest. We're now depending on the average singular value divided by the smallest, which is better. We have paid in that we have an n in front. But this method, each iteration is way cheaper than doing, in terms of computational complexity, than doing a matrix vector multiply. Instead of being, for a dense matrix, instead of being n squared, it's like linear and n cost. Okay? So these can lead to methods. If you do the full runtime analysis method, you get n squared times sigma bar over sigma n times log 1 over epsilon, which is better when you have decaying eigenvalues, because the average singular values, the average singular value should be much better than the max. Okay. So it's also doing better when you have outlying singular values. One thing, yeah, I will briefly go through this. There are very close related methods called randomized coordinate descent methods. They can almost just be viewed as like rearrangings of the Kaczmarz methods that achieve almost exactly the same bounds. So there's a paper by Leventhal Lewis on these, which also uses random sampling to choose coordinates to update. Let's not worry about it. For the experts here, like one thing you might complain about with these methods, and it's really an issue in practice, is they don't effectively take advantage of matrix vector multiplication. Like they just pluck out one thing at a time. So they're not, even if they win in terms of computational complexity, they're typically slower in practice. But there are a lot of block variants of these algorithms that are being studied that can become much more competitive with Krylov subspace methods or potentially beat them. Anyway, where am I going with this? There are even more methods that can do better when you have outlying singular values. So one thing that we've worked on a lot is methods where you do preconditioners. Joel's going to talk about preconditioners, I think, might talk. Okay, if you have heard anything about randomized linear algebra, one of like sort of the crowning results is like sketched preconditioning. People work on, I'm not going to do the details, low-rank sketch preconditioners that also get bounds, which are better when you have small number of outlying eigenvalues. Here's a complexity theoretic problem. What is the best algorithm? Is it CG? Is it the Kaczmarz methods? Is it coordinate descent? Is it the sketch preconditioning algorithms? To ask that question, all of the bounds are incomparable to each other. You need to establish a benchmark. So like one line of work I'm like a fan of in recent years is by Michal Derzinski. He asked this question, and you can frame it in many ways. There's just one framing, which I think is a reasonable one. If I'm given a linear system that only has k outlying eigenvalues, meaning except for the top k, singular values, except for the top k singular values, the system is well conditioned. So in particular, sigma, this is inverted. Sigma, no, that's right, sorry. In particular, sigma k plus 1 of A divided by sigma n, so the k plus first singular value divided by the smallest, is less than c for a fixed constant c. For that specific class, what's the fastest algorithm you can get? And so using sort of a variety of these methods, sketch preconditioning, Kaczmarz, like block Kaczmarz, people have sort of whittled away on that question till a very recent paper by Michal and Aaron Sidford, which gets runtime except up to logarithmic factors, roughly n squared plus k to the omega, which is pretty amazing. Like n squared is what you would get if your matrix was perfectly conditioned, like order 1 conditioning, and they're just paying that plus like a marginal cost to get rid of those top eigenvalues in the matrix. Nice bound for a simple to state problem. Yeah, go ahead.
What's the dependence on c in here? Like n squared times c?
I don't know, but when c is a constant, it's constant. But there will be some dependence on c.
It's basically the same as you would have the dependence on the condition.
Oh, good. So just multiply by c.
Yeah.
Okay, good.
N squared times c plus kappa to the omega?
Yep.
Yeah. I should say their paper deals with more general problems. It's just like the simplest to state bound. But like one thing that I think is really nice about this line of work is it actually led to faster algorithms for a really clean linear algebraic problem. So here's a problem. You have matrix A, you want to compute the Shatton p-norm. The Shatton p-norm is the LP norm of the singular values in the matrix. So like if you want to do the L1 norm, L1 norm is just, yeah, that's right. The L1 norm is, that's fine. That's what people would call the nuclear norm. And the question is, how efficiently can I compute that up to multiplicative accuracy? So nailing the nuclear norm, computing it very precisely, or any Shatton p-norm, probably costs n to the omega time. You probably have to do an eigendecomposition and add things up. But can you get multiplicative accuracy faster? And what this result led to is an n squared times poly 1 over epsilon time algorithm for getting 1 plus epsilon multiplicative error to any LP, to the Shatton 1 norm, and then there are also improved bounds for Shatton p norms. So like clean linear algebraic question that this sort of like line of work on improved bounds for linear systems was able to solve. It is randomized, yeah, it's randomized. And like previously, the best algorithms, this followed from a paper from my brother and some other people that gave an n to the 2.11 time algorithm. Or sorry, yeah, plus some improvements. Okay, I'm out of time and it's lunch. So I think I will not say much more. Very briefly, the biggest thing I missed in this talk is I didn't talk anything about structured systems. There's a lot of people in this room who work on structured systems, like rank structured system, hierarchical matrices, things you can apply fast multipole methods to, displacement structured systems, graph structured systems. So a lot of people are interested in fast solvers for Laplacian systems, symmetrically diagonally dominant systems, which have had huge impact in theoretical computer science. I was going to talk briefly about these. Roughly, the way I would think about this slide without the details is people pick out a class of systems and develop fast algorithms for it. So one that was really important in theoretical computer science because it led to faster algorithms for some of our fundamental problems, like max flow, min-cost flow, other cut and flow problems, was solving Laplacian systems, which means solving a system where A is the Laplacian matrix of a graph and generalizations of that. You can think of that work as sort of ending. They solve this class, it's done. Move on to your next class, try to find another thing. One sort of like interesting complexity theoretic like angle you can take on these structured classes is I don't think we have very good connections between them. So there's not much work on understanding, does fast algorithms for your favorite class imply anything for my favorite class? Does it imply anything for general linear systems? So one sort of vignette of a result along these lines is by Rasmus King and Peng, which said that, no, not Peng. That's her first name, Peng Zhang. Yeah, this is Peng Zhang from 2017, which says that if I could solve systems in a slight generalization of the class of Laplacian systems, so this includes like multi-commodity Laplacians or truss-distance matrices or what are called total variation matrices. It doesn't matter what they are, they're slight generalizations of Laplacians. In order m to the alpha time, where m is the number of non-zeros in the matrix, that would lead to algorithms with comparable complexity for solving any linear system with m non-zeros in it. So this can be viewed as either like a conditional hardness result or an algorithmic approach, right? Like if you're gonna solve this slightly bigger class, which still looks very structured, you're gonna solve everything fast, which you could view as a good thing or a bad thing. Maybe it's a reason not to work on the problem. You're gonna give the problem to your PhD students. Maybe you should work on it. So yeah, I hope that gives you a flavor of like sorts of questions you can ask in the space. Yeah, that's it. Thanks, guys.
Questions, comments, please?
Yeah.
I was wondering about the models for proving unconditional lower bounds. So you introduce this model with the work of the matrix vector multiplication, very clean, simple, cute model, but it doesn't seem to capture this Krylov methods and other things.
That captures block Krylov because you can choose the
matrix multiplication can be done without matrix vector.
Oh, because you could say the matrix is cheaper. Yeah, that would be one way to generate a model. You could say like for free, I can do any matrix multiplication where like.
Yeah, I have it like, I don't know, I have some prices. So I was just wondering if there are like well-studied models. Which,
no, but that's very natural. Like you could have a cost model. It gets more, it's always a trade-off, right? Either it's simple and it's easy to prove things, or you make it more complicated, it captures the real world, and it becomes much harder to deal with. But that could be a reasonable trade-off, right? Like make some function of like what it takes to do a, multiply your matrix by b vectors and then try to develop complexity in that model. Yeah, it's not a bad idea. Yeah.
Could you comment on the structure, the state of the art of algorithms for matrices with the displacement structure, as you mentioned?
I actually don't know. Not like an area I know anything about. So I can't comment on it. Yeah.
So for the latest results, like the later half of the presentation, you present asymptotic optimal arithmetic bonds. For these methods, do you care about the error analysis? Like whether they are stable or?
Yeah, I mean, yeah, there's a question of like, do you care or do you work on? Like, I don't work on those things, but it's certainly something we should care about, because if any of the methods are going to be used in practice, we need to care about them. And I think like this is in another very interesting area of research. So, like one thing here is people in my area, which is like roughly randomized linear algebra, really interested in sketch and precondition methods. And then people notice that like depending on how you implement these things, it can really affect the final error. Like you need to actually be really cautious about it. So a lot of people, like Ethan in this room is the person who's worked on it the most, have then taken those methods and tried to understand, can I actually get like very fine-grained control on the final error in finite arithmetic? So yeah, it's really important to care about, and it's I think of often the algorithm comes first, and then we need to think about the numerics a lot before it can move into practice.
I don't know how to capture this, but in practice you almost never solve a dense linear system where you have complete access to the matrix, right? That just
sure, yeah.
Happen, right?
Yeah.
It's structured, but like you pass quietly from the matrix vector model towards like a dense linear system.
Yeah.
And I'm wondering what kind of problems this is actually capturing, because I mean, you cannot even hold that dense matrix.
Right. So, for example, for like the Schatten norm problem, I'm like writing everything as if it was dense. Part of the reason I'm doing this is for simplicity. So those algorithms sample rows of the matrix, and if you have a matrix where some rows can be much denser than others, they'll be slower. But in the model where the rows of the matrix are all S sparse, you could have replaced like the n's there, the n squareds there, with n times s. I believe. Yes, that's correct. So yeah, it does, but I'm just doing that for simplicity. But yeah, that's an important difference between the Kaczmarz methods and the coordinate descent methods. Like, if you actually want to get bounds that involve MV of A, or like, you need to have uniform sparsity across the rows or columns. Yeah, yeah.
If I may attempt to answer the question about displacement structure, and again, I'm not the world's authority on this, but people who are Vadim Olshavsky and Victor Pan has some work on this. Also, there's a nice survey by Boston. I'm not sure where the stress goes there. So it's relatively recent, and certainly the complexity of matrix multiplication is involved in those bounds. But the n is not the n which corresponds to the size of the matrix. It corresponds to sort of the sizing of your displacement.
Thank you.
Yeah.
Sorry, let me just correct what I'm. So, I guess some of the results you mentioned here do have this property where if it's like uniformly sparse matrix, then you get an improved bound. I don't think this one specifically is.
Okay, good. So open question.
I think
can you get this ns replaced by n squared would be nice.
And I believe that should be possible.
Yeah. Okay. Awesome.
And also I think that the sort of finding models of computation that sort of sit in between matrix vector, and you have a matrix given is a very interesting.
Yeah, that's a good point.
Okay.
Yeah.
Good. It's about time for lunch. So I should suggest more questions.
Yeah,
in
I'm
the
taking it
lunch break,
offline. Yeah.
so